I completely shut off my heat when it was minus 11 degrees Fahrenheit outside for an entire 24 hours in order to prove a point. My home's heating system, a furnace which was installed and spec'd for the structure by professionals in the HVAC industry, is way too big for my home. Why did it get installed? I can only speculate, but it means that my current heating system absolutely should not be considered as any kind of baseline when it comes time to replace it. And many of you are probably in that same boat. If you are looking to make a change to your home's heating and cooling system, especially if that change is moving from one heating technology to another, it pays to find out what heating and cooling capacity you actually need for your home. And the good news is that it's not that hard anymore. Before we get to that though, this is a tweaked and condensed version of a longer video on my main channel. If you'd like some additional context and plenty more runtime, you can check that out there or through the link in the description. And I'd like to begin this version by letting you in on a secret the industry doesn't want you to know. I'm not really joking, despite the cliche. Here goes. Those fancy heat pumps they keep talking about on the news? Well, it turns out those heat pumps are just air conditioners. That's all they are. They're just air conditioners equipped with an extra valve, which allows them to operate in reverse to produce heating in addition to cooling. That's all that a heat pump is. Everyone in the HVAC industry knows this. At least I sure hope they do. But because heat pumps are hyped up right now and people are interested in them, in areas where they haven't been common, they are often painted as fancier and more exotic machines than they really are. The only truly new things on the scene are cold climate heat pumps, which operate efficiently even in very cold weather. But those just have little tweaks to the underlying technology and are not fundamentally different from the commodity equipment that's been getting installed the world over for decades. So watch out for price gouging. It's rampant right now. And for reference, poke around on HVAC wholesale sites to get an idea of how much more a heat pump system should cost compared to a new furnace and air conditioner. You'll quickly find out it's not much at all. If you already have an air conditioner and furnace, the most expensive and frankly only different task when installing a heat pump is running a new circuit for backup resistive heating. And that's not always even necessary anymore depending on your local climate or your backup heat source. There's a lot of nuance here, which I'm skipping over for time, but bottom line, $20,000 quotes to install a heat pump are ridiculous outside weird circumstances. But this video isn't so much about price gouging, it's about figuring out how much of a heat pump or other heating system you actually need. I live in a fairly new townhome in the Chicago area. Because it was built to recent codes and I'm sharing walls with neighbors, it's pretty energy efficient. Yet, whoever spec'd its heating system was apparently not given the memo. It's been equipped with a bog-standard 60,000 BTU per hour furnace and 2-ton air conditioner. The air conditioner, miraculously, is actually close to right on the money. But the furnace is way too effing big. It is barely running even in extreme cold. How do I know that? Eyes and ears are pretty helpful here, but even more helpful is the fact that I have a smart thermostat. Since I have a simple single-stage heating system which is only ever heating at its full output or not heating at all, a log of how much time it's spent heating in a day could be used to determine how much heating output it actually produced that day. And wouldn't you know it, the smart thermostat logs what it tells the furnace to do over the course of a day, and my user account retains that data for well over a year. So with a quick look in my thermostat's app, but not the Nest app, the Google Home, don't get me started, I can look back in time to see what it did on any particular day. So let's do that. Here's what a typical winter day looks like weather-wise. January 5th was a cloudy day with the temperature hovering right around freezing point. With essentially no help from the sun, my furnace was providing the only heat to keep the house warm, and it needed to run for 3 hours and 10 minutes total. That right there makes it obvious the furnace is much bigger than it needs to be, but this is Chicago. It gets a lot colder than just freezing. Like 2 Christmases ago. December 23rd, 2022 started out at a balmy -8 degrees, which is -22 for those who speak metric. Despite it being that frigid though, the furnace only ran for 6 hours total. 6 hours of 24 in the day is only 25%, or 1/4 for those of you that speak fractions. Running only a quarter of the time in weather like that suggests the furnace is in fact 4 times larger than it needs to be. Now, I wasn't home that day. That's good in that there weren't any other sources of heat like cooking appliances or hot water usage to skew the data, but it's bad in that the set point was only 62 degrees and not what I normally keep it at. Since it can get a bit colder than -8 degrees around these parts, and since normally I keep it a little warmer when I'm at home, I'll go ahead and fudge that and say my furnace is 3 times oversized. Since my current system produces 60,000 BTUs per hour, then apparently I only really need 20,000 BTUs per hour of heating available, which in heat pump speak is not even 2 tons. That's pretty wild. If that's true, then I actually need about the same heating output in the dead of winter as I need cooling output in the hottest parts of summer, which admittedly feels kinda wrong. In the winter, I have to fight an 80 or 85 degree temperature differential in those Arctic blasts, but we rarely ever crack 100 degrees in the summer, and most of the time, we're only fighting a 15 or 20 degree differential. But, well, the data doesn't lie. However, there are some reasons to be cautious. Firstly, while my furnace is rated for 60,000 BTUs per hour, that's actually its input rating. It only releases 92% of the heat energy in the gas it's burning into my home, the rest is wasted in the exhaust, so in reality its output is slightly less. But that's presuming it's working correctly, which I don't have a way to confirm. It could be outputting more heat than it's designed to. There are also 2 other minor sources of data fuzziness which reduce the accuracy of a data logging thermostat. The raw energy content of natural gas varies somewhat from day to day, so even if I knew for a fact that my furnace were operating perfectly, its actual heat output won't be quite consistent. Also, the thermostat logs how long it calls for heat, but at every startup, there's actually a delay while the furnace goes through its ignition sequence, so the thermostat is slightly over-reporting total energy output. Now, to be clear, these little sources of error are little and unlikely to amount to much. Plus 2 of them work in my favor anyway. But it does mean that my 20,000 BTU per hour conclusion probably isn't perfect, especially because I fudged it a bit to account for not being home. I still know my furnace is wildly oversized no matter what, but I wanted to know exactly what sort of heat I needed in extreme weather. And I knew a trick to find out. Just get a bunch of space heaters. See, since heat is heat, you can convert between units as much as you like. 20,000 BTUs per hour is equivalent to 5.86 kilowatts. And an ordinary space heater like this can pump out 1.5 kilowatts. So, assuming my thermostat data and math are correct, simply running 4 space heaters on high, which would produce 6 kilowatts of heat, should actually provide more than enough heat to keep my home warm, even in the most extreme weather we ever get. So, I thought, why not just wait for some extreme weather and then try that and see if it works? So I did! But I used more than 4 heaters, and the setup was rather involved and pretty risky. So first, let me just say, don't try this yourself. I took a number of big risks designing and performing this test. I could have ended up with frozen pipes if I wasn't careful, and I put myself at risk of a fire using the space heaters, particularly because getting enough heat distributed in enough places required the use of extension cords, splitters, power strips, and even Christmas lights. Yeah. To save on time, I'm not going into all the considerations I had to make for the test. You can check out the main channel video if you want more of those details. But the bottom line was, I had about 6,500 watts of resistive heat distributed throughout my home. The heat sources were powered through digital temperature controllers, so I could properly maintain a consistent temperature with them, and they were all metered through energy monitors, so I could total up how much energy was actually used during the test. I set up each temperature controller to maintain the same temperature band that my furnace normally does in each room when set to 69 degrees, and with the setup finalized and in place, all that was left to do now was reset the energy monitors, turn on all those heaters, and shut off the furnace. So that's what I did. The test began at 8 a.m. on January 14th, when the outside temperature was minus 11 Fahrenheit or minus 24 Celsius. With the furnace disabled, the heaters would have to hold their own. Before long, the temperature controllers had switched them all on, but then they all started going off. This meant that the heaters were sufficient to raise the indoor temperature, despite it being 80 degrees colder outside than inside. So clearly, that 6.5 kilowatts of heat on tap was more than enough. And 24 hours later, the heaters had used a grand total of 110.76 kilowatt hours, representing an average power draw of only 4.61 kilowatts, or 15,729 BTUs per hour. Now, the whole 24-hour span included some sources of noise. For one, it was a bright sunny day during the test, so the sun was helping to heat my home a bit, and I did prepare food, which added some heat not accounted for by the meters. However, I was taking readings from all the meters every 4 hours, and between 8 p.m., long after I made dinner and the sun had set, and 8 a.m. the next day, just after sunrise, the heaters used 61.38 kilowatt hours, representing a continuous draw of 5.115 kilowatts, or 17,452 BTUs per hour. The outdoor temperature during that period was fluctuating between minus 9 and minus 11 degrees, which is just a teensy bit warmer than the coldest temps we typically experience. So, there we go. That's the number. 17,452 BTUs per hour is the actual heating load of my home when it's minus 10 outside and about 70 inside. Which means that sure enough, my furnace is triple oversized. Actually a bit more than that. For me and my home, this is excellent news. Because I'm in a townhome, which was built assuming everything that could be gas would be gas, I only have 100 amp electrical service, which is limiting. But even using resistive heat, as I did in the test, I only need just a hair over 5 kilowatts to stay warm, which is only a 20 amp electrical load. A heat pump will use even less power so long as it can operate with a coefficient of performance above 1, which these cold climate heat pumps can do well into negative temperatures. So when it comes time to replace my furnace, a 2-ton heat pump, which can normally produce 24,000 BTUs per hour or 7 kilowatts of heat, will be just fine, and 5 kilowatts of backup heat strips will be more than enough to supplement the heat pump when required, or even function as my only heat source in an emergency. But my experiment, although it was extremely valuable, was also absurd. It is not a thing anybody should do, and the good news is, nobody has to. You might find this hard to believe, but those scientists? They've figured out the thermal properties of the materials we use to build our homes. Insulation has an R value, which tells you its resistance to heat transfer. Windows have R values too, plus low E coatings on the glass help reduce solar heating in the summer and reduce radiant losses in the winter. The materials on the exterior of the home have an influence too, and we know all this information. To tie it all together into something useful, there are these tools out there called measuring tapes, which allow us to gauge the size of walls and windows. If you actually take the time to assess these variables, you can perform a load calculation, which will tell you how much heating and cooling your home actually needs, depending on how it was built. Now, I am not here to show you how to do one. It's not that complicated. You're essentially just finding the total area of your home's exterior surfaces, taking note of window and door dimensions too, then plugging that information along with their R values into a spreadsheet. And don't forget to count the ceiling and floors too. But it is pretty tedious. Still, for grins and giggles, I did one for my home. I used an online Manual J calculator. Manual J is essentially the industry standard for how to do a block load calculation. And after inputting all my measurements, it told me that I would need 19,000 BTUs per hour of heating with an outdoor temperature of -15 and an indoor set point of 70 degrees. That's within spitting distance of what my experiment just showed. And since it was a little warmer during the test than -15, coming in a tad higher than my experiment makes perfect sense. So rest assured, those calculations do, indeed, work. If someone had actually done that calculation and believed its results, they would never have put a 60,000 BTU per hour furnace in my home. That's just way more than my home needs. But I can feel your trepidation coming through the screen. Why would I conclude that having just enough heat would be enough? Well, enough is by definition enough. When a heating system is properly sized to a given home, then when the weather outside gets frightful, the heating system will need to run non-stop, and that is actually normal. There's a concept called design temperature, which is important here. Where I live, -15 outside is about the coldest we ever experience, and 70 degrees inside is the warmest I'd ever need my primary heating system to keep the house. Those are my design temperatures, the absolute worst conditions a heating system should expect to fight, and they only show up once or twice a year, if that. There isn't actually a need to have any more heat capacity available than what the design temperatures dictate, especially when, even if the weather happens to dip below the design temp, a wide variety of simple supplemental heat sources, such as all those space heaters I now own, are available to fill the gap. But actually sizing heating systems appropriately seemingly never happens. The HVAC industry is currently stuck in a habit where they build tremendous amounts of margin into a home's heating system. To be fair to them, there are some good reasons to do that. When you only have a single source of heat, then when the weather hits design temps, a properly sized heating system will take a long time to increase the temperature if, say, you're like me and like to turn the heat down a bit at night. But the main reason they're always going so overboard is that that's easy. Particularly when you have gas at your disposal, you can just use simple rules of thumb, such as a home's footprint and number of floors, to pick out a furnace. Then choose the next size up just in case. I can all but guarantee that's how my home ended up with such an oversized heating system. But this habit needs to die. We're not going to be heating our homes with gas forever. Pick whatever reason you'd like. There are plenty. Heat pumps are in the news so much these days because they allow us to capture ambient heat energy from outside, concentrate it, and move it inside. That process is so efficient that we can end up with 3 or sometimes even 4 times as much energy inside our homes than we spend running the heat pump to collect it. That is why they are such a big deal. It's a way we can get more heat with less energy expenditure, and doing more with less is always a good idea. For that reason alone, more and more people will be using heat pumps as their primary or possibly only source of heat. They just make way too much sense to not use. And when speccing a heat pump system, actually installing the correct equipment with the correct capacity is very important, more than it's ever been. There are a whole bunch of reasons that this is the case. For one, heat pumps are electric sources of heating and cooling, so larger systems require more electrical capacity to run them. Therefore, concluding that you need a bigger heat pump than you actually do can come with a whole host of potential headaches, including the need to upsize circuits or potentially even get a service upgrade. So you absolutely don't want to go overboard. Plus, if you want a backup generator or even a whole home battery system, which are getting more and more popular, bigger heat pumps will need bigger generators, batteries, transfer switches, and all that jazz. Having more than you need can be a legitimate problem. Plus, I keep running across folks who have been told by HVAC contractors that their home's current ductwork isn't big enough to have a heat pump. Maybe that's true, but if that contractor hasn't done a load calculation or any sort of sanity check on whether the home's current heating system is actually appropriate, then that contractor simply doesn't have enough information to be making that conclusion. Those ducts may be perfectly fine for the heat pump that's actually appropriate for that home. Additionally, and this is something that everyone in the industry should know very well, oversizing a heat pump can lead to nasty moisture problems in the summer months. If you have too much cooling capacity, the heat pump might short cycle, and that means it won't run long enough to actually dehumidify the air. What I personally think the industry needs to get more comfortable with, quickly, is that secondary heat sources will become much more common as we transition to heat pumps. And those are going to function as the margin that traditionally gets figured into gas-fired systems. I mentioned backup heat strips previously. Those are just old-fashioned heating elements, not unlike the wire elements in these space heaters, that get tucked into the air handler to provide additional heat. They are often referred to as auxiliary heat or emergency heat, and both of those terms are apt. The heat strips provide an emergency backup in case the heat pump fails, but if the heat pump is working, they can work alongside it to boost the total system output when required. If configured correctly, then when the temperatures are approaching design conditions and the heat pump is only barely adequate, the thermostat can command the heat strips to work alongside the heat pump to perhaps double the system output and quickly raise the indoor temperature when requested. And even if the temperature dips below design conditions, meaning the heat pump is no longer sufficient on its own, modern cold climate heat pumps don't just stop pumping, they'll keep on working well into the negative temperatures. They probably won't be putting out much heat, but it will be something, so the heat strips won't be working alone. In other words, there is still a margin. It just looks a little different now. So to recap, first of all, heat pumps are not magic machines. Don't let anyone convince you they're revolutionary technology. They're just reversible air conditioners, and they should only cost marginally more than a conventional heating and cooling system to purchase and install, with the only major potential hiccup being provisions for backup heating if necessary. If you're getting a $20,000 quote for a central heat pump, ask why on earth it's so high and what sort of equipment they'll be installing. Then poke around on those wholesale sites to see if their bid makes any sense at all, or if they're just playing amateur economist and testing to see just how far they can push what the market will bear. For those of you that don't have central heating systems, ductless mini-splits are going to be great options, but they are going to be more expensive because they involve more work. Still though, the equipment itself isn't very expensive, and the work isn't really that involved. I've done it myself, and I'm just some schmuck on the internet, so shop around. Second, nobody should ever be sizing replacement equipment based on what is currently installed. Depressingly often, what's there now is oversized up the wazoo and blatantly inappropriate for that home, especially when a home is on its fourth or fifth system. Imagine how out of control it can get when each installer just keeps jumping up to the next size, just in case. There are many, many ways to do a sanity check on that equipment, but it rarely ever happens. Just this past spring, my parents got a cold climate heat pump, and the sales rep who came out somehow figured they'd need a 5-ton heat pump based on, as far as I can tell, nothing but a guess and maybe the output of their old system. But had that rep looked at the data from Nest, he would have seen that their old system had never run for more than 12 hours in a day, so it was about double oversized, and a 3-ton heat pump, the same size as their existing air conditioner, would be sufficient. Luckily, I was there for this process, showed him that data, and he listened to me. And sure enough, their 3-ton heat pump is working just fine, and the heat strips were only required once this winter, and for just a few hours at that. If you've got a smart thermostat, the historical data it provides can be tremendously useful. HVAC professionals really ought to be looking at that data when it's available, and when it's not, They need to be doing proper load calculations. That needs to be way more common than it is right now. And somebody, perhaps even the Air Conditioning Contractors of America, the publishers of Manual J, should really build a guided tool to help professionals do this quickly. Bottom line, the tactics of yesterday are no longer appropriate. Everything is changing, so habits need to as well. Frankly, if you are in the HVAC business, you could really differentiate yourself from your competitors by 1, actually investigating the performance of the equipment that's already there to see if it's correct, perhaps by looking at thermostat data if available. 2, performing even just basic load calculations to check that you're somewhere in the ballpark. 3, educating your customers on how heat pump systems work and how the heat strips help to fill in any gaps. And most importantly, 4, charging honest prices for heat pumps, which will, get this, cause you to win all the bids. Honestly, this industry is ripe for disruption, and it doesn't need to come from outside. One of you just needs to wake up and smell the roses. Change is scary and difficult, but one of the great things about heat pumps and electric technologies in general is that they are incredibly flexible. It's not just fire in a box with air blowing through it. It's a modular toolkit which can be configured in many ways and tailored to any home. And they're only going to get better and better as time goes on. Already, they are appropriate in climates like mine, which was unheard of not that many years ago. So why not learn some new tricks? Isn't that what makes life fun? Thanks for watching, and more pumping, more now.